Yeah, welcome. So the topic we'll be discussing in this lecture is deletion in a B tree. Right? So in this lecture I will be explaining you the algorithm, and probably in the next lecture we'll be discussing with an example. So to delete a particular key value, first we have to identify the key to be deleted. Okay. So the objective is to delete the key with X. Okay. The objective is to delete the key X from the B tree, right? So to delete, first you have to identify that key where it is available in which node in the B tree, that you have to identify, because in a B tree you know that a node can have more than one keys. So first locate the identify, or you can say locate the key X, right? Suppose while searching, if key X is not found, then nothing to delete, then you can say there is nothing to delete and you can come out. If X is found in some internal node Z, so whatever the key we want to delete, it may be either in the internal node or it may be in a leaf node. If it is in the internal node Z, then X will be replaced with its in-order successor or with its in-order predecessor. In-order successor is the smallest value in the right subtree of that of that key value, and in-order predecessor is the highest value in the left subtree of that particular key value. And this in-order successor or predecessor, surely it will be available only in the leaf node. Okay. So in-order successor or predecessor, it will not be available in any internal node. It will be in a leaf node. Okay. So now we have to delete that particular in-order successor or predecessor with which we have replaced. Okay. So the problem of deleting a non-leaf node, problem of deleting a key, problem of deleting a key from a non-leaf node is transformed into the problem of deleting a key from a leaf node. Okay. So the point to take away is, we are going to delete only from leaf node. We are not going to delete from any internal node. If there is a situation, if there is a need to delete keys from internal node, then those keys will be replaced either by their in-order successor or by their in-order predecessor, and then we'll be deleting those in-order successor or predecessor which will be surely available only in the leaf node. Okay. Next we shall see how to delete a key from a leaf node, because in all cases we are going to delete only from the leaf node. Okay. Assume that the key X is available in the leaf node P. Assume that the key X is available in the leaf node P. Okay. But say that P is also a root node. So P is also a root node. It means there is only one level in the tree. There is only one level in the tree, and there is only one node, and that node itself is the root node and the leaf node, and the key is available in this node. Okay. Now there is only one node, and that is the root node, and also that is the leaf node. So whatever the key, you just check the key and we can delete that key. That's it. We can check and delete that key. Okay. After deleting, if the tree is left with at least one key, then it is fine. Then still the tree is not empty. Okay. Still the tree is not empty. Okay. Our job is done. And also we can say that the tree is not, it is not empty. Okay. But at some situation, after deletion, the tree may become empty. Assume the tree contains only one node, and that node contains only one key, and that is the key you want to delete. Then after deleting that key, then the B tree will become empty. Okay. This is the case if the key X is available in a node P, and if node P is the root node, and also if it is the leaf node. Okay. Right. So the rest of the cases we'll be discussing when P is not root, but when P is leaf. Okay. There are three cases, right? So case 2, what it says in the sense, we have identified the key X in a node P, which is not a root node, but it is a leaf node. It is a leaf node. Okay. And say that after deletion, if P has at least seal of m by 2 minus 1 keys, then we need not do anything. We can just delete it. Okay, because what is the minimum number of keys allowed for any node other than the root node in a B tree? The minimum number of keys allowed is seal of m by 2 minus 1. Okay, minimum child is seal of m by 2. Okay, so minimum keys is seal of m by 2 minus 1, right? So after deletion, if the node P has seal of m by 2 minus 1 keys, then we need not do anything. Our job is done. Okay, that is case 2. Case 3, you have identified the key X in a node P, and P is the leaf node. Okay, now after deletion, if the number of keys in that particular node P, if it will become seal of m by 2 minus 2 keys, if it will become seal of m by 2 minus 2 keys, then that is called as a deficient condition. Then that is called as a deficient condition, because minimum there should be seal of m by 2 minus 1 keys in all nodes other than the root node. Okay, but now P has seal of m by 2 minus 2 keys, which is a deficient condition for B tree. Okay, now this deficiency should be removed. So how this deficiency can be removed? There are two ways to remove the deficiency. What are the two ways? This deficient node P can borrow a key either from its immediate left sibling or from its immediate right sibling. Okay, it can borrow a key from one of its nearest sibling, that is either the nearest left sibling or the nearest right sibling, provided those siblings were having at least seal of m by 2 keys. Okay, then only they can donate. Why? Because only if they have seal of m by 2 keys, after donating, it will become seal of m by 2 minus 1 keys. Okay, so if any of the nearest sibling is having minimum seal of m by 2 keys, then they can donate. Otherwise they cannot donate. Okay, if donate or borrow, whatever it may be. Okay, so if such donation happens or such borrowing happens, then we say that we will perform a rotation. Then we will say that we will perform a rotation to balance the B tree. Okay, so here balancing means what? P has become deficient. That is it has seal of m by 2 minus 2 keys. That deficiency should be removed. Okay, we will ensure that the deficiency is removed. That is called as balancing. For that we perform rotation. Okay, right. Now the node P can borrow the key either from its right sibling or from its left sibling. Okay, so how it will borrow from the right sibling and how it will borrow from the left sibling, that we will see. Okay, so say that node P's right sibling has at least seal of m by 2 keys, then it can donate. Okay, so the right sibling of P has at least seal of m by 2 keys. Okay, now the right sibling is going to donate to the left sibling, I mean P. Okay, so the right sibling we are calling it as Q. Okay, so P is in the left side and Q is in the right side. Okay, so Q is going to donate to P. So the donation is happening in which direction? It is going in the direction of left. Okay, so we say that is a left rotate. We say that there is a left rotate. Okay, here in this rotation, parent also involved. It does not happen just between P and Q. P is the one which is deficient, Q is the one which is going to donate. Okay, and the and in this process, parent of P and Q also will be involved. Okay, so first we will locate the parent of P and Q. Let R be the parent of P and Q. Okay, let R be the parent of P and Q. Okay, in R you have to identify the key Ki. Okay, key Ki in R such that R is a parent of P, right? R will have many keys. Okay, from R you have to identify that particular key of parent. I mean, from R you have to identify that particular key. R itself is the parent. Okay, such that left of that particular key, the left pointer of that key is pointing to P, and the right pointer of that key is pointing to Q. Okay, such a key you have to find out. Okay, right. Now our donation is going to happen in which direction? In left direction. Okay, Once you have located that key ki, copy that key ki to p. Okay, that is to the node p which is deficient. Okay, now p will have what? P will have more. P previously having seal of m by 2 minus 2 keys. Now p got one extra key. Okay, and that extra key surely it will be added in the right end, because it is coming from its parents. It is coming from its parent node. Okay, and parent node's key whose left pointer is pointing to p. Okay, so that key ki will be surely greater than all the values in the p. Okay, so it will be coming in the right end of p, right? Okay, so after copying this, now now in the parent or ki, the key ki will be replaced with the smallest key of q. So q is the one which is donating, or q is the one from which we are borrowing. Okay, so q is the right sibling. So the right sibling will donate its left key, will give its left key, and that will replace ki. Okay, now the left sibling, I mean now the smallest key of q will be removed. Smallest key of q will be removed. Okay, fine. So this is how donation, I mean borrowing or rotating uh, in left happens. Okay, say okay. So say the second case, the node p can also borrow from its left sibling, provided the left sibling has at least seal of m by 2 keys. Okay, in that case the borrowing or donation happens from left to right. Okay, it is going towards right. It is going towards right. Okay, so we call this as right rotate or rotate right. Okay, here also we have to identify the parent or. So let or be the parent of p and q. In or, identify a key ki. Now you see q is in which side? Q is to the left and p is to the right. Okay, identify key ki in or such that left of ki is equal to is pointed by q, and right of ki is pointed by or. The right of ki is pointed to p. Okay, left of ki is pointing to q, and right of ki is pointing to, I'm sorry, left of ki is pointing to q, and right of ki is pointing to p. Okay, the reverse of that case. Okay, so now we are going to rotate in the right direction. Okay, so first what we are going to do, copy ki to p, right? So now ki will be copied to the left end of p, because all values in p will be greater than ki. Okay, so if a new key, if the ki comes, it should occupy the left end of p. Okay, it will be the leftmost key in p, right? And replace ki in or with the largest key of q. Okay, and the largest key of q and the largest key of q will be removed from q. Okay, so this is how we perform right rotate, right? But this is possible if p is deficient and if at least one of its sibling can donate. One of its nearest sibling can donate, or they can give borrow, they can, or p can borrow from them, right? So after doing this, the deficiency is removed. Okay, so different authors use different terms. Some of them call this as rotation, some of them call this as borrowing. Okay, but the textbooks follows the rotation, so here I am calling it as rotation. Okay, let us go with rotating. Fine. Then case 4. Case 4, what it says in the sense, after deleting that particular uh, key x from p, p has seal of m by 2 minus 2 keys. That is p is not deficient. Okay, p is deficient. That is p is deficient. Okay, that is, it is supposed to have seal of m by 2 minus 1 keys, but it is having seal of m by 2 minus 2 keys. So p is deficient. Okay, and its nearest sibling has exactly seal of m by 2 minus 1 keys. So it means it cannot borrow. So it means p cannot borrow from its nearest sibling, because its nearest sibling has only seal of m by 2 minus 1 keys, which is the minimum keys required. So it can't borrow from them. So what should we do? So we should so now in this case we should merge. We should merge or we should combine. We are going to combine two nodes. Okay, right? So how we are going to combine, that we will discuss. Okay. So now P is deficient and P cannot borrow either from its left sibling or right sibling, because both its left sibling and right sibling, or whatever the nearest sibling available, they have exactly seal of m by 2 minus 1 keys. So it can't borrow. So we should go for something called as merge and combine. Again, some of the authors call this process as merge, some call this as combine. Actually, textbooks uses the word term combine. Okay, fine. So now P is deficient. Now how we will merge? So what we will do is identify the nearest sibling of P, okay, either left or right, merge P and Q. Merge P and Q. Okay, we are going to join the two nodes. So it is not just we are merging P and Q, here also we should involve the parent. Okay. So in the parent we should involve that particular key. In the parent we should involve that particular key such a way that P is in between, such a way that that key uh, identifies that key ki which is in between P and Q. Again the same logic, such a way that if q is the if q is the right if q is to the right sibling of P, then you have to identify such a ki, you have to identify that ki such a way that ki is left pointer is pointing to P and ki is right pointer is pointing to Q. Okay. If Q is the left sibling, then identify such a key ki from the parent such a way that ki is left is pointing to Q and right is pointing to P. Identifying ki is same. Okay. Now bring that ki also down. Ki also down. So we are going to merge P, Ki and Q. Okay. We are going to merge what? We are going to merge these three things in this order. In this order, if Q is the right sibling, we will merge as P, Ki, comma Q, and then we have to sort. Anyway, we have to sort it. Okay. And if Q is the left sibling of P, then we will be merging as Q, Ki, P. Okay. So it depends where Q is there. Accordingly, the merging happens, but Ki will always come in the middle, right? After merging, the new node will have how many keys? The deficient node, which is P, has seal of m by 2 minus 2 keys. Okay. Its sibling has seal of m by 2 minus 1 keys, and one key is coming from the parent. Okay. So totally there will be 2 into seal of m by 2, 2 into seal of m by 2 minus 2 keys. Okay. This is minus 2 minus 1 plus 1. This is minus 3 plus 1, which is minus 2. So there will be 2 into seal of m by 2 minus 2 keys. Okay. And this value will be surely less than or equal to m minus 1. It cannot exceed m minus 1. Okay. Because the maximum keys allowed in a node is m minus 1. Right. Okay. As per B-tree norms. Okay. But after merging, what happens? One key is reduced in OR, that is in the parent. In the parent OR, one key is reduced. Okay. So you have to check whether the parent has become deficient or not. If parent is not deficient, then you can leave it. Deficient means parent should have minimum seal of m by 2 minus 1 keys if it is not a root node. Okay. If it is a root node, it is enough if it is have even 1 keys. Okay. So you have to check whether it is not deficient or not. If it is not deficient, you just leave it. Okay. Suppose if the parent has become deficient. Okay. If parent is the root node and if it is deficient, in the root node, deficiency means what? No keys, because even in root node one key is also allowed. Okay. In the root node, deficiency means no keys. Okay. In that case, if there is no key in the parent, then you can just discard that particular key. Okay. You can just discard that particular in that case you can just discard that particular node itself. Okay. Because there is no key in the root node. Okay. And the merged node, the new node will become the root. Okay. After merging, if R is deficient and if R is not the root node, okay, then it means R is some internal node. It is not root and also it is not leaf. It is some internal node. So it is having seal of m by 2 minus 2 keys. Okay, it is having seal of m by 2 minus 2 keys. So then it means that this internal node is deficient. Now this deficiency should be removed. Now how it can be removed? So again the same process. first you should try to perform rotation. So for rotation you have to check the OR sibling, whether OR sibling can, whether this node OR can borrow from its sibling or not. It can borrow from its nearest sibling if the nearest sibling has at least ceil of m by 2 minus 1 keys. So if such a sibling is available, then it can borrow. Okay. If borrowing is not possible, then again you have to go for merging. Okay, then identify the nearest sibling and merge OR with its nearest sibling along with the appropriate key of the parent. Okay, so after doing that, again you have to check whether the parent has become deficient or not, right? So this process may continue up to the root node. Okay, or this process should continue either until all the deficiencies are removed or until you reach the root node. Okay, fine. So this is how the algorithm for removing a particular key or deleting a particular key in a B tree works. Okay, so in the next lecture we'll discuss an example for this. Fine, thank you.